A car with wheels of radius 19 inches is designed to last for 150,000 kilometers. Taking 1 inch to equal 2.54 centimeters, obtain an order of magnitude estimate for the number of complete rotations a wheel will undergo in such a lifetime. So we're going to start by working out what one rotation of the wheel would be. So basically that means the distance around the wheel or the circumference of the wheel. So the formula for circumference of a circle is 2 pi r. So we're going to multiply 2 pi by the radius, which is 19. But since 19 is in inches and we're interested in centimeters and 1 inch is equal to 2.54 centimeters, we're going to multiply that also by 2.54 centimeters. Because ultimately we want to change that then into kilometers because we're dealing with kilometers up here. So 2 pi times 19 times 2.54 centimeters will give us the circumference or the rotation of one wheel. And what we're going to do with each of these three numbers is round it off to 10 to the power of something. So we know that pi is approximately 3.14, and multiplying 3.14 by 2, we can round off to 10 to the power 1. So 3.14 times 2 is 6.28, which rounds up to 10, which is 10 to the power 1. 19 also rounds off to 10 to the power 1, because 10 to the power 2 is 100, and 19 is clearly much closer to 10 than it is to 100. And then 2.54, we're going to round off to 10 to the power 0, because 10 to the power 0 is really 1. And 2.54 is closer to 1 than it is to 10. Then 10 to the power 1 times 10 to the power 1 times 10 to the power 0 is 10 squared, because 1 plus 1 plus 0 is 2. So the circumference of the wheel is 10 squared centimeters. But remember, we're interested in kilometers. And to change centimeters to meters, we divide by 10 squared, which is 100. And then to change meters to kilometers, we divide by 10 cubed, which is 1,000. So we're going to divide that 10 squared by 10 squared multiplied by 10 cubed. Again, the 10 squared representing the centimeters changing to meters, and the 10 cubed representing the meters changing to kilometers. And 2 plus 3 is 5, so you get 10 to the power 5 for your denominator. And then 2 minus 5 is minus 3. So you get 10 to the power minus 3 kilometers. And this is the circumference of the wheel. So 10 to the power minus 3 is really 1 times 10 to the power minus 3 in scientific notation or standard form. And what we do is we take the number 1 and we have the decimal point after it, and we move it 1, 2, 3 places to the left and put our new decimal point. So we have 0.001. So this is really 0.001 kilometers. Next, we're going to write the distance in scientific notation or standard form. So the distance was 150,000 kilometers, and that can be written as 1.5 times 10 to the power of 5. And that can be rounded off to 10 to the power of 5. And the reason for that is 1.5 rounded off to 10 to the power of something would be 10 to the power of 0, because 10 to the power of 0 is 1, and 1.5 is much closer to 1 than it is to 10. And 10 to the power of 0 times 10 to the power of 5 still just gives us 10 to the power of 5, because 0 plus 5 is 5. So this rounds off to 10 to the power of 5 kilometers. So we know the distance and we know the circumference. So in order to figure out the number of rotations of the wheel, we just divide. So we're going to divide the distance by the circumference. So 10 to the power of 5 divided by 10 to the power minus 3 gives us 10 to the power of 8, because 5 minus minus 3 is 5 plus 3, which is 8. So the number of rotations is 10 to the power of 8. Thus, the number of rotations is the order of magnitude 8. Part 2. By rounding to two significant figures, obtain another estimate. So by the same idea, we want to work out the circumference of the wheel. So it's going to be 2 times pi times the radius, which is 19, times 2.54 centimetres, which gives us 303.23 centimetres, which rounds off to 300 centimetres, correct to two significant figures. Now I know you might look at this and think, well, 3 is the only significant figure there, but 303 rounded off to two significant figures, the closest is 300, so we actually take that middle zero there as a significant figure. And 300 centimetres is 3 metres, which is 0.003 kilometres. So again, to change from centimetres to metres, we divide by 100. And to change from metres to kilometres, we divide by 1,000. And 0.003 kilometres is the same thing as 3 times 10 to the power minus 3 in scientific notation or standard form. So this is correct to two significant figures. Although there is only one significant figure, we do take the other 0 to be a significant figure. So again, the distance is 1.5 times 10 to the power 5. And again, we're going to divide for the number of rotations. So we have the distance, which is 1.5 times 10 to the power 5, divided by the circumference, which is 3 times 10 to the power minus 3. And 1.5 divided by 3 is 0.5. And 10 to the power 5 divided by 10 to the power minus 3 gives us 5 minus minus 3, which is 5 plus 3, which is 8. However, for scientific notation or standard form, the decimal point must be after the first digit. So we need to move this decimal point one place to the right so that we get 5. And if we do that, we're going to reduce the power by 1. So we get 5 times 10 to the power 7. Part 3. By calculating the correct value, determine the percentage error in the answer in part 2. So again, for the circumference, we're going to multiply 2 by pi by the radius, which is 19, by 2.54. And we're going to divide by 100 times 1,000. The 100 being changing it into meters and the 1,000 then changing it into kilometers. And you end up with 0.003032265. The distance again is 1.5 times 10 to the power 5 kilometers. And dividing by the actual circumference, we end up with 49,467,968.22. So this is the number of rotations. Now we want to work out the percentage error. So the formula for percentage error is relative error multiplied by 100%. The formula for relative error is absolute error divided by true value. And the formula for absolute error is going to be true value minus the estimate. And these lines represent modulus, so we take the positive value. So the number in green, 49,467,968, is the true value. Then we're going to subtract the estimate from part 2, which was 5 times 10 to the power of 7, which is 50 million. So subtracting those and taking the positive value gives us 532,032. So this is the absolute error. Now to get the relative error, it's the absolute error over the true value. So the relative error divided by the true value. And then to get the percentage error, we just have to multiply that relative error by 100%. And we get 1.08%. So the percentage error is 1.08%.